Hello. So I just wanted to pick up where we left off today, which is we had talked about the three methods for finding limits. We said that we had already looked at the numerical approach. That was where we had the table of x values approaching the one that we were interested in, both from the left and the right. And we would just find out what those f values, the function values, approached, and that's what we would say the limit was at that particular point. Then we said the graphical approach, where we looked at the graph of the function, and we said, okay, it looks like it's approaching this point. And then the third was analytic approach. And again, we're going to look at that in a lot more detail in the next section. But for right now, we just need to go in a little bit more depth about limits and some other aspects of them. So we're going to look at this example right here and how we can find out when limits might not actually exist. Right, and again, if I just can refresh your memory here, this was from the first page of our notes, and we said that if f of x becomes arbitrarily close to a single number L, right, so it's a number, not a concept or anything, it's a number. So as it gets closer to a single number L as x approaches c from either side, then the limit of f of x as x approaches c is L. So we have to have them approaching that value c from, actually I would say both sides it has to agree on, but for right now we'll say either side, and it has to approach a finite number. All right, we'll talk about infinite ones later, but right now we're going to say it's got to approach a finite number. All right, so then in this we're going to see one way that the limit could not exist, and that is if on opposite sides of that value c right here, the graph is doing something different. All right, so let's take a look at this function right here and graph that. And this will be a treat. We've not really looked at anything like this before. We've looked at absolute values, we've looked at transformations of absolute values, but to have it be an absolute value of x over an x, we've never looked at that. So let's think about what that would look like. So if I take the absolute value of x over x, there's two things that could happen. One is that x would be greater than 0, all right, a positive number. And the other thing that could happen would be x would be less than 0. Obviously x could be equal to 0, but we don't really care what it is at 0. We just want to know what's happening in around 0 on either side. All right, again, it's not what's going on specifically at that value, but what everybody on either side of that value is saying. All right, so we want to see what happens when x is greater than 0 and when x is less than 0. So let's think about what happens to this function when x is positive, and specifically what happens in an absolute value when x is positive. All right, so hopefully you're thinking about that, and you're thinking, when I put in a positive number, so let's say 6, if I take the absolute value of 6, what happens? Well, you should say, I get exactly that same number out. So when x is greater than 0, the absolute value bars do nothing at all. All right, it's already positive, and so it keeps the same value. So when x is greater than 0, absolute value of x over x is the same thing as x over x, because the absolute value bars do nothing, it just preserves the value. All right, and so x over x is just 1. All right, so anywhere where x is greater than 0, this is going to be the constant function 1. All right, so we can come over here and we can say, well, anything greater than 1, or sorry, anything greater than 0, it's going to have the value of 1. All right, now let's try it again. When x is less than 0, so say we plug in something here like -2, what happens when we take the absolute value of it? All right, you should say, I get the positive version. So when I put in -2, I get the positive value out. The way we say that is whatever the value is, we just change it to its opposite. So if I put in -2, I get out the opposite of -2. So we would write that when I plug in a negative value in here, I get out the opposite of that value. And then in the denominator, I still have x. All right, negative x over x is negative 1. So anywhere where x is less than 0, it's just going to be the constant function negative 1. All right, so anything less than 0 is going to give us that. All right, so then we try and take the limit. So we say, all right, as x values are approaching 0 from the left, this is very consistently negative 1. And as x is approaching 0 from the right, it's a constant positive 1. All right. So again, if you remember that example that we did earlier where we had the constant graph where it was just plain old 1 except at 2 where it was 0, and then it went like that. This differed from what everybody else said that it thought it should be. They thought it should be 1, all right? And 2 was like, I'm just going to be 0. In this case, it's everybody on this side does not agree with everybody on this side. So imagine you've got your volleyball friends and your church friends. Your volleyball friends are saying you should be negative 1, and your church friends are saying you should be positive 1. Since they cannot agree, we would say that the limit does not exist. All right? So since the function values differ on each side of 0, the limit does not exist. And I'm going to write DNE for does not exist. All right, so, and it says show that the limit doesn't exist. That's what we just did. We showed on the values greater than 0, or on the positive side of that x-axis, it's 1 everywhere. And on the left side, or the negative x-axis, it's negative 1. And so it can't agree. So we would say in that case, the limit does not exist. Right, this is an example that we're going to see frequently. So if you were a little bit confused by this, I would say go back and watch this again. Hopefully seeing it a second time will help, or at least let's talk about it in class. Okay, the second thing that could go wrong is that the graph does not stop at a number L, a fixed or finite number L. So let's take a look at this one. All right, so if you think about what that looks like, we've graphed 1 over x before. All right, so this is going to be very similar to that. All right, but let's just pick a couple values. And again, we're not choosing 0 because it's going to make it undefined there. But let's say we put in 1. So at 1, it will be 1. Let's say we put in 1/2. If I square 1/2, I get 1/4. So 1 over 1/4 would give me 4. So at 1/2, it's up at 4. And then if I plug in 2, 1 over 2, that's going to give me 1/4. And so on this side, it'll look like this. And then on the left side of 0, since we're squaring it, again, in 1 over x, we end up with something like this. All right, in the first quadrant and third quadrant. But here, because we're squaring, we're still going to end up in that our y values are going to be positive. And so we're just going to end up with the mirror image of this. So at -1, it's 1. At -1/2, it's 4. And at -2, it's 1/4. Something like that. Okay. And so what we're going to say here is that since as we approach 0, the x values approach 0, either from the left or the right, it doesn't matter, they do not approach some finite number. It's not like we can say, oh, they approach 10. No, because as soon as I keep getting closer to 0, I square that value and take the reciprocal of it, and it's going to make it go up and up and up. The closer I get to 0, the higher the value is going to go. So I'm going to say here, because f of x is not approaching a real number L, as x approaches 0, the limit does not exist. All right, so first case is if they don't agree as we're approaching from the left and from the right. Sorry, I did that in the reverse order, from the left and from the right. The second is if they grow in an unbounded manner. And the third is called oscillating behavior. For homework, I'm going to ask you to read that example, but let me just give you a quick sketch of it right now. And that would be as I approach 0 or some other finite number, doesn't always have to be 0, the graph is going to do something like this. And it's just going to go crazy here and just keep going up and down, and then it's going to start going off, something like that. All right, so it just keeps going up and down so much that we can't ever pin it down. And again, they're going to show you an example of that in the textbook, which I'm going to ask you to look at, because their picture is far better than mine right here. All right, so again, just to summarize, 3 types of behavior that are associated with the non-existence of a limit, or in other words, we would say the limit does not exist. F of x approaches a different number from the right side of C than it approaches it from the left side of C. F of x increases or decreases without bound as x approaches C. That was our 1 over x squared example. And then f of x oscillates between 2 fixed values as x approaches C. And again, you'll see that one in the textbook. Okay, so I'm going to eraser things out of here. Okay, formal definition of a limit. All right, so again, imagine that you want to go out with your friends and your mom says, as you're leaving, don't be late. And you were like, okay, cool, I won't be late. And you get home at 1:30 because you think that's not that late. And your mom is really mad because she said, that is totally late. And you're like, no, 2:30 would be late, 1:30 is not late. And she said, I thought you were going to be home by 11. It's because you did not define that time that was, quote, too late, right? And so the same thing can happen with limits. So to avoid that misunderstanding, we're going to formally define that. So here's the formal definition of a limit. Let f be a function defined on some open interval containing c. Again, remember, c is an x value. So let the function be defined in an open interval containing that, except maybe not at c. Again, think about that first graph we did together where at that value 1, it was undefined there. So imagine c was 1 right there. So we'd say in a little window around 1, the function was defined, all right, but not at that value of 1. And let L be a real number. And again, back in that example, our limit was 3. So let L be something like 3, just some real number. The statement that says the limit of the function f of x as x approaches c equals that value L. So again, in that first example that we did together, c is 1 and L is 3. So when we said the limit of that function as x approached 1 is 3, right? And again, in general, the limit of some function f of x as x approaches some random value c equals L, some random value of a y value equaling L. That means that for any epsilon greater than 0, there exists some delta greater than 0, so that when c is within, or when the x value is within delta units of c, then the function is within epsilon units of L. Now, this is going to be so much easier to imagine what's going on if we draw a picture, all right? So let's draw a function. So again, I'm going to have it framed here. So we've got this window right here, and let's say that this is our function. All right, we're going to call that f of x. All right, so f of x is a function defined in some open interval that contains c. So here's, let's say this is our x value, c right here. So it's defined in some open interval around that. All right, and again, the function might not be defined at c. So again, up here, instead of drawing a solid dot there, let's draw a hollow dot because we don't necessarily know that it is defined there. All right, so again, very much like this one right here that we talked about before. So let f of x be a function defined on an open interval that contains c. except it might not exist at C, and let L be a real number. Again, L is the limit, so that's this y value over here that we're going to say that the function is approaching that y value as our x values get closer to C. All right, so this is, we're setting the stage right here. F is a function defined in an open interval around that x value, and LB is a real number that we think is the limit right there. So when we say the limit of f of x as x approaches C equals L, we mean that for any epsilon greater than 0, so when you see epsilon greater than 0, anytime you see epsilon, you should think it's a small number, right? So when you see epsilon, think small. All right, so for any positive value of epsilon, any really small positive number epsilon, there exists some number delta greater than 0. Again, when you see delta, think small. So we're talking about 0.05 or 0.001, tiny numbers. All right, so any epsilon, for any epsilon greater than 0, there is some delta greater than 0, so that whenever my x value, the distance between my x value and C is less than that small number delta, then f of x is, the distance between f of x and L is less than epsilon. Right, so whenever I'm in a little delta window around C, right, so that means the distance between C and here is delta or less. So let's call this a little delta window. So this is going to be C plus delta, and this is going to be C minus delta. Right, so whenever x and C are less than delta apart, right, that's what that means. Whenever x and C are less than delta, so x's are all going to come from in here, not from out here, because that's greater than delta away from C. Right, then the function must be less than epsilon units away from L. All right, so I'm going to draw this little window right here and follow it up. And then what that means is that I must be within a little epsilon bubble around L. So that means I must be in this little window that is epsilon units away from L. Right, so here's my C value. This is where it hits the graph, or it appears that it would hit the graph. And then this is the value of L. So as soon as I'm within a little bubble, delta width wide on either side around C, then that means I must be in a little tiny epsilon window around L, so that I'm just really, really close to it. So again, as I get closer and close to it, it means that this window is so tiny that it doesn't matter, that it's just going to be really close to whatever that value is. I can't be approaching C and have it end up be somewhere around here. That's outside the window. All right, so let's be a little bit more explicit right here. So when I say in here, or not I didn't make up this definition, f of x becomes arbitrarily close to L. Right, and again, that was an expression that I think we used on the very first page of our notes. No. We read it somewhere. I can't find out where it is. But anyway, when we say f of x becomes arbitrarily close to L, then that means that we've got some little window, or that the difference between them is less than some small number epsilon. The reason I'm putting the absolute value signs around here is because I have no idea whether f of x is going to be higher than L or whether it's going to be lower than L. So I'm just putting these absolute value symbols around here just to make sure that this is positive. Right? So if it were negative, then it's always going to be less than epsilon. So we make sure that it's always positive so that we can say, yeah, definitely it's less than epsilon. And that means something because this is a positive value less than a really small positive value. Right? And then when we say x approaches C, again, this is kind of, like the conversation with your mom. It's just a little too loosey-goosey, just like becoming arbitrarily close to L. It's too loosey-goosey. We want to define that. So when we say x approaches C, what we mean is that the distance between x and c, again, it doesn't matter which one is larger or smaller, we're taking the absolute value to say that we just want the distance between them. And we say that's less than delta. All right. This side of it means that x cannot be equal to c, that it has to be something in this little window around it, but not equal to c. Right, and this is saying that x is within delta units of c. All right, so again, here's our very formal definition, and then these are the phrases that we say when we're just kind of saying, you know, again, that don't be late thing. Arbitrarily close. Everybody's idea of arbitrarily close is different. So when we say that, here is how we're going to nail them down to say, this is what we mean, that there is some epsilon that is going to bound the difference between f of x and L whenever it's in a little window that's delta wide around C. All right. I never have loved this definition. It makes me think really hard, but we'll see how we use it. All right, so we're going to do a couple examples here. I think just 2 examples, and then even though there's, no, maybe, yeah, 2 examples. Even though there's a third, we're not going to do the third one. All right, so it's asking us, given the limit of 2x minus 5 as x approaches 3 is 1, find a delta such that absolute value of 2x minus 5 minus 1 is less than 0.01 whenever 0 is greater than the absolute value of x minus 3, which is less than delta. Don't freak out when you see this. We're going to do a couple of these and you'll get to the point where you're like, oh, these are totally easy. All right, so again, we're going to remember what the definition says, that if I have this condition right here, then this follows. All right, if I have this condition, then this follows. So let's look at what they give us. First they say, we're saying that this is true, that the limit of 2x minus 5 as x approaches 3 is 1. All right, so first of all, let's look back here and say, what is playing the role of f of x, what's playing the role of c, and what is playing the role of 1? All right, so hopefully you're thinking f of x is 2x minus 5, c is 3, and L is 1. Agreed? Okay, so then let's also look at these things right here and see where they're getting these things from, because right now they look kind of like they're just pulled out of thin air. All right, so it's saying find a delta such that whenever 2x minus 5 minus 1 is less than 0.01, sorry, absolute value of that, where are these numbers coming from? All right, well, if we look up here, this is f of x, right here, minus L, and this is just the delta, the epsilon value, right here, and then x minus 3, well, obviously the x, but the minus 3 is the c value, and there's the epsilon, or sorry, I keep saying in the reverse, there's the delta. All right, so these are the things that are coming from the definition. That's why they chose them. They're not random. They're filling in the values that go along with this limit right here. All right, so it's saying find the delta such that whenever our epsilon is less than 0.01, or so that we can guarantee that the difference will be less than 0.01 units away whenever we're in that delta bubble around 3. All right, and again, this looks like it should be crazy, but it's not going to be. Let me just erase this to make a little bit more room for us. All right, now we're going to do 2 things. We're going to kind of do a cheater's method here, although it's not a cheater's. Everybody does it this way. What we're going to do, so we're supposed to find that delta, and we're going to work backwards to find the delta. We're going to start with this, where we've been given a lot of information. So actually I should write up here that epsilon is 0.01. We didn't fill that in right there. So we're given that epsilon is 0.01. and we want to find delta. All right, so we're going to start on this side, and we're going to start with this. All right, and we're going to work down until we figure out what we should choose delta to be. And then we're just going to pretend like we never did this. All right, this was on scrap paper. And we're just going to start with the delta that we chose. And it's going to make it look like we pulled it out of thin air, but really it's because we worked backwards to get it. All right, so this is kind of our scrap on this side. And this is going to be our somewhat like a proof that we've done what they asked us to do. All right, so we're going to start with this, and we're going to simplify as much as we can. All right, so we've got the absolute value in there. Sorry, that looked like a 1. All right, so think about what you would do in here to simplify that. All right, hopefully you would say, well, I would just combine like terms, and so this would become 2x minus 4 is less than 0.01. Nope, I'm totally kidding there. 2x minus 6 is less than 0.01. All right, now I see that they both have a 2 in common. I'm going to do more steps this time than we normally will do. So I'm going to write this as 2 times x minus 3. It's less than 0.01. Eventually you're not going to do that step in here, and you're just going to break this up. And again, I'm doing this step right here. There is a rule that we talked about a couple of years ago that said that if I have some positive number or some multiple in here, like a scalar inside, I can break that apart. So this can become 2 times x minus 3, each in their own separate absolute values. Not true for addition, but it is if I'm multiplying something. All right, so I couldn't break the x and the 3 up in here because that's a difference. But because it's a product here, either a product or a quotient, we can break it apart into 2 separate ones. All right, now absolute value of 2 is just 2, and so I have just x minus 3 left in there, less than 0.01. Right, I'm going to divide both sides by 2, and so I end up getting absolute value of x minus 3 is less than 0.01 divided by 2. Well, this is 1/100th divided by 2. So this ends up being times 1/2, or 1/200th. Wow, that is 0.005, I think. Yeah, 0.005. Okay, now you might think, great, what the heck did that do for us? Well, look at what we're trying to do. We're trying to show that we're within a delta bubble of 3 right here. And that's exactly what we got down here just by working backwards, that we got x minus 3 is less than 0.005. So whenever we're 0.01 units, whenever the distance between the function and the limit is less than 0.01, we are less than 0.005 units away from 3. Right, so this is what we're going to choose as delta. All right, so again, this is our scrap work. Nobody's going to see it because when we come up here, we're going to say, let delta equal 0.005. And people are going to be like, dang, you just pulled that out of thin air. But no, we didn't. We did our work on this side to get that. Okay, so now we're going to start up here and we're going to say, okay, let delta be 0.005. So what it says is that whenever this distance between x and 3 is less than 0.005, so we've got this. All right, so now we're starting with this. All right, and now we're just going to work our way down until we get to this. So basically what we're going to do is start here and go backwards. Again, this is the scrap that we're not sharing with anybody. We've just done this kind of backwards method to get the value of delta that we want, and then we're going to work our way up. So we think, okay, what did I do to get from here to here, and how can I reverse it so I get from here to here? Well, to get to this point right here, we divided both sides by 2. So now let's just multiply everything by 2. And again, that means multiplying 0 by 2, which doesn't do anything. It just does that. Multiplying this by 2. and multiplying this by 2, which is going to give us 0.01. All right, then we think, well, how did I get from here to here? And then I'm just going to do the reverse. So again, this was several steps. So let's just skip this step right here. And we'll just say that we can move that 2 into the absolute value signs without any penalty here. All right, so this is absolute value of 2 times x minus 3 is less than 0.01. And then again, how did we get up to here? Well, it's just we distributed the 2. All right, this is the part where I'm happy to have this step still written out because I might not think to change this into that, but we have it at least written out so we know that we should have 0 is less than 2x minus 5 minus 1. All right, again, negative 6 can be written as negative 5 minus 1, and that's less than 0.01. And again, I'm going to put this in parentheses right there. All right, so we can show that if we pick delta to be 0.005, that we are within 0.01 units here when we're looking at the distance between f of x and the limit. All right, so again, we just start with something like this. We work our way backwards until we get to the delta that we want. We pretend we didn't write this, and we just start here, and we look amazing because it looks like we just thought of that and it worked perfectly. All right, let's do one more example of this. We're not going to do example 8, so we'll just do this one. All right, so use the epsilon delta definition to prove that the limit of 3x minus 2 as x approaches 2 is 4. And again, let me just remind you what we're doing. It says that if 0 is less than the absolute value of x minus c, which is less than delta, then the absolute value of f of x minus L is less than epsilon. Let me write these at the top right here for you. So it's saying if 0 is less than the absolute value of x minus c, what is c in this case? All right, hopefully you said 2. Again, c is that number right there, and it's less than delta. Then, all right, the next part says that f of x, what's f of x in this case? All right, hopefully you said 3x minus 2, minus L, again, that's this, is less than epsilon. All right, now notice the difference between the last one and this one. In the last one, they gave us a value for epsilon. Sorry, they gave us a value for epsilon, and we just had to find the delta. This time, we're just doing it in general, and so we're not given a specific epsilon value. We're just going to find a delta that is related to epsilon. In other words, it's expressed in terms of epsilon. So it won't be expressed in terms of something like 0.01, like half of 0.01. It's going to end up being expressed as in epsilon. Okay, so again, we're going to do that same thing. All right, so it's saying if the distance between x and 2 is less than delta, then this has to be true. So we're going to start with the conclusion, not with the hypothesis, and we're going to work our way down until we get something that looks like this. All right, so we're going to start with 3x minus 2 minus 4, absolute value, sorry, these keep looking like 1s, is less than epsilon. Again, epsilon is just something small. So just think of something small in your head. Okay, so again, like last time, let's just combine like terms. So we've got 3x minus 6 is less than epsilon. All right, again, I've got this 3 that I could factor out of this expression right here. So I'm going to do two things. I'm going to factor it out of here, and then I'm going to pull it out of the absolute value sign. So I'm going to write it like this. 3 times the absolute value of x minus 2 is less than epsilon. All right, again, intermediate steps where I factored that out, and then I pulled it out. Again, it's only because this is being multiplied by this that I am allowed to do that. Do not try this at home if it's adding or subtracting. This right here, if I tried to break that up into absolute value of x minus absolute value of 2, that is completely false. All right, doesn't work. And if you don't believe me, try it with different numbers for x and verify that it is not true. And it doesn't even matter that it's a minus. The same thing would happen if it were plus. It's just not true. Okay, so we're right here. Again, let's stay focused. We need to get to the point where we've got something like this. Absolute value of x minus 2 is less than delta. And so think about what we can do to get this to look more like this. All right, hopefully you said, oh, let me just divide both sides by 3. And so I get x minus 2, absolute value of x minus 2 is less than epsilon over 3. All right, so I'm going to say, I'm going to choose delta to be epsilon over 3. All right, remember when we got to this point in the last problem, we had 0.005, and I said, okay, let's choose delta to be 0.005. Now here we're going to say the same thing, choose delta to be this, but now we're expressing delta in terms of epsilon. So regardless of whatever I choose for epsilon, if it's 0.05 or 0.00001, it doesn't matter. All I have to do is take a third of that, divide it by 3, and that's what I should choose for delta. All right, so up here, I'm going to look really smart, and I'm going to say, let delta equal epsilon over 3. And again, you can choose anything that you want that's smaller than epsilon over 3, but it's easiest if we pick that because it's very easy to reverse our steps. Okay, so then we end up with, all right, so let delta be epsilon over 3. So if 0 is less than x minus 2 is less than epsilon over 3. All right, again, think about what we did to get from here to here, because now we're going to have to go backwards. All right, so we multiplied everything by 3, so then we get 0, because 3 times 0 is 0, is less than 3 times absolute value of x minus 2, which is less than epsilon. And then again, we can smush that back inside because it's multiplication. Again, if it were addition, subtraction, couldn't do it. So this becomes absolute value of 3 times x minus 2 less than epsilon. Distribute. Right, and again, this is why I'm particularly happy to have this work here, because I would forget already by the time I get here how I need to write it. Again, you could cheat and look up here. 0 is less than 3x minus 2 minus 4. I'm just breaking up the negative 6 into negative 4 and negative 2. Or negative 2 minus 4. All right, and then I'm just going to write it as this 3x minus 2 minus 4 is less than, less than epsilon. All right. We'll do more of these together, and you'll do some for homework. But for right now, hopefully that's okay. Oh, there's one other thing I want to point out. Let's go back to here, because I forgot to write this. I just want to remember to say this. 2 things. One is the statement that the limit as x approaches c of the function f of x equals L. This implies that the limit exists and that it equals L. So this tells us 2 things. One is that there is a limit. We don't have any of those things that are associated with the non-existence of a limit. So it doesn't approach a different number from the left and right. It doesn't increase or decrease without bound as we approach C, and it doesn't oscillate. So when we say that, it implies that the limit exists and that the limit equals L. All right, so that statement packs 2 things in there. The limit exists and it equals L. The second thing I wanted to say and forgot to is essentially, and again, this is just my words, first tell me how close you want to get to L. And then I'll tell you which delta to pick. All right, that kind of summarizes what we did on the previous page. You tell me how close you want to get to L. Again, that's what's going on here. I want to get to 0.01 units away from L. And then I'm going to tell you which delta to pick. Right, and so that's exactly what we did. We said we wanted to get within 0.01 units of L, and then I told you to pick 0.005, or we figured out that's what it was. Same thing here. I told you I wanted to get within epsilon units of L. Again, this is a in general, not a specific one, and I told you what delta to pick. All right, so that's kind of the idea here, just in a broader sense. You tell me how close you want to get to L, and then I will tell you which delta to pick. All right? Hopefully that's helpful, and we'll talk more in class.